Hello, this is Professor Keen, and welcome back to my lectures on electricity, magnetism, and light. In this series of lectures, I'm talking about the experiments by Hans Christian Oersted that he published in 1820, in which he describes his work on the effect of a current of electricity on a magnetic compass needle. In the last lecture, I talked specifically about his experimental apparatus, which consists of a galvanic cell, a battery essentially, attached to a wire, and he ran an electrical current through this wire and noticed that it had an effect on a magnetic compass needle. There's an apocryphal story that I'm not sure if it's true, but it's a nice story anyhow, so I'll tell it. The idea is that Oersted was having a dinner party where he was showing off to his friends that if you pass a sufficiently large electrical current through a wire, the wire turns red hot and glows. This is what all of us scientists do at our dinner parties. It sounds like a lot of fun. And he noticed out of the corner of his eye that when he did so, there was a compass needle nearby and there was a small turn or deflection in the compass needle. And he noticed this but didn't make a big deal of it at the dinner party, but later on he went back and started redoing the experiments, and that is how he ended up making the discovery that he did. Anyhow, we described this first experiment that he carried out in my last lecture, and let me remind you the apparatus consisted of a battery. I'm going to draw schematically this battery like this. I'm going to make it look a bit like a car battery. This isn't exactly like the one he used. His looked more like a bunch of trays of acid sitting on the floor with copper and zinc plates sticking out of the top. He had this battery, and then he had this wire that he called the uniting wire, and it ran along in the north-south direction. So I'll put some compass directions right here. That would be the eastward direction, west, and southward direction. And this was propped up in his laboratory on a couple of stands that looked a bit like this. He doesn't have, as I mentioned in my last lecture, he does not have any drawings in this text, so we have to imagine what it looked like. And then this was attached via these connecting wires like this. And the positive terminal of the battery was here, and the negative terminal was right there. And then he noticed when he hung a compass needle beneath this, ordinarily the compass needle points in the northerly direction, but when he attached the wire to the positive terminal, what happened is this compass needle swung in this direction. It swung, oops, I drew that in the wrong way. So it swung in the westward direction like this. Okay, so that is what he noticed. That's essentially the experiment that he carried out. Well, let's talk about some of the variations. This was the first experiment he carried out. Now, the question might arise immediately, is this deflection of the compass needle, can it be understood in terms of simple Coulomb attraction and repulsion? I mean, we already know that positive charges repel each other, and negative charges repel each other, and positive and negatives attract. So maybe this is just some interesting manifestation of something we already knew by virtue of Coulomb's law. So what does he do for his second experiment? This is a variation on the first experiment. For the second experiment, what he does is he, instead of suspending this from a string, he just kind of mounts it on top of a bracket of some sort. That still allows the compass needle to turn, but then he moves this wire to the east and to the west above this compass needle. So let me draw a top view of how I imagine this looking. So if he takes this compass needle that's below this wire, and so the wire, this is the top view, this is hooked up to the positive terminal of the battery, this is the negative terminal of the battery, so this bottom part is this end of the wire, and the top is the right end of the wire. So this is a northerly direction, like that. And if he slid this off to the right, this compass needle is still pointed kind of in this direction. And he says, well, maybe this is because this wire overall is acquiring a positive charge. So suppose the wire itself, the uniting wire, is acquiring an overall positive charge. Okay, so I'm going to draw a positive sign in the wire to indicate that this hypothesis is acquiring a positive charge, and maybe this compass needle is turning this way because the tip of the compass needle is positively charged and the back of the compass needle is negatively charged. So when you try to run an electrical current through this with the battery, it becomes positively charged, and this is turning because it's repelling the positive charge on the tip of the compass needle. Maybe that's what's happening. Well, if that is what was happening, then if you moved the wire off to the left side, that is, you moved it more west in the westerly direction, what should happen? Well, then this compass needle, as you move this wire to the left, to the west, then the compass needle should swing back in the other direction, because after all, moving it left or right shouldn't change whether or not the wire has an overall positive charge. So if we move the presumably positively charged wire to the west of the compass needle, the needle should reverse. So all of the things being the same, now the compass needle that had been pointing, the tip had been pointing westward, it should now deflect to the east, because after all, we were hypothesizing that the tip of it was positive, that the back was negative, so when we move this thing off like this, it should swing the other way. But this is not what happens. He notices that when you move this off to the left, you're keeping it above it, the needle is still pointing in the same direction. So this is not what happens, and so he concludes from that the Coulomb repulsion is not an adequate explanation of the deflection of the, I guess, westward deflection of the compass needle beneath the wire. Okay, you can kind of see how he's thinking about this. Okay? So there's something else going on here, something stranger going on here. So he continues. Let's talk about his third experiment. Okay? Where is this, by the way? If we look at the text, this appears on the... we are about at the top of page 78, bottom of page 77, and top of page 78. And in this section, what he does is he replaces the wire with different kinds of material wires. So he tries wires made of different materials. Okay, so he mentions that he tries wires that were constructed of platinum, he uses gold, he uses silver, he uses iron, so platinum, gold, I'll use the chemical symbols, silver, he uses iron wires, he uses some other alloys like brass and zinc, I think, and he notices that when he does so, you still get the same effect. You still get, or he still got, the same deflection of the compass needle. Although with some different wires, the effect was less pronounced. So, but with, in some cases, somewhat less pronounced results, or pronounced turning, or as he was called, pronounced declination, pronounced turning of the needle. Okay? And he mentions that even if you break the circuit, this loop right here, by interposing a bit of water in a cup, you still get the same effect. So imagine you took this wire and you took, once again, this battery, and you had these terminals on the battery, and you hook the wire up like this, and this end of the wire that's at the positive terminal of the battery, you dip it into a cup of water. Okay, so let me get my color here. So you put some water in this cup, like this. So now you've got water in the cup. And the other wire you dip in the same water and you attach it. Well, in this case, you still get the turning of this compass needle, but it only works if you have these wires quite close to each other in the water. So he says, I think if you only have them separated by just a couple of inches, then you still get the turning of this compass needle. If you have the wires too far apart, then you do not get the turning of the compass needle. Okay, and presumably what's happening is these different materials in some way resist the amount of electrical current that can flow through the wire. So you might imagine if this is a positive terminal, negative terminal, you're going to get some electrical current, I'll call it I, this electrical current through the wire. And when you use different materials that have less conductivity, then it diminishes the amount of electrical current through the wire, and that reduces the size of the effect he's talking about. But as long as you have electrical current that's sufficiently large, you still can get a deflection of the compass needle. I think what I'll do is in my next lecture talk a little bit more about the relationship between the electric potential that the battery produces, the voltage the battery produces, the amount of electrical current through the wire, and the resistance of the material. So I'll do a little bit of a digression into that next time, and then we'll come back and talk more about some more of Oersted's experiments.